Now, a structured question, define the term boiling point. So you are able now to define the term boiling point. Remember what we said, it's not a point, it's a temperature at which the vapor pressure is equal to the atmospheric pressure. What is the relationship between the strength of intermolecular forces and boiling point? We talked about this one to say as the strength of intermolecular force increases, the boiling point increases. You cannot say directly proportional. We don't use that here in paper 2. We say now as the strength of intermolecular force increases, the boiling point increases, not directly proportional. We use that nicely in paper 1. It works well. But here, let's stick with increasing the strength of intermolecular force. Increase with the boiling point will increase as well. The relationship between the strength of intermolecular force and boiling point is investigated using 4 organic compounds. So we're given 4 organic compounds, A, B, C, D. I would like to advise you here that when you are given compounds as A, B, C, D, propane, propane-2-one, propan-1-ol, and propanoic acid, when you write, it's better to talk about A, B, C, D than having to talk about the entire structure, because sometimes it becomes too much. So I find it easier to talk about compound A, compound B, compound C, compound D, because they are given there. Now refer to the type. The question is channeling you to say that when you answer, refer to the type and strength of intermolecular forces to explain the difference in boiling point between compound A and B. Now, if you check compound A and B, the type for compound A, propane, we said is London forces. For propanone is dipole. So you will first write the intermolecular forces that we get to say A has London forces, B has dipole. Now, the second thing, you talk to the strength of intermolecular force. Definitely, B has stronger intermolecular force than A. You see the importance of B and A now. B has stronger intermolecular forces than A. And then the one that has strong intermolecular forces, we are saying more energy will be required to overcome the intermolecular forces in B than in A. So you are able to answer in that way, and you will get your 3 marks. When it comes to 3.2, compound C and D, we are saying now for compound C and D, we are talking about an alcohol and carboxylic acid. Those are relatives, remember, because we are saying an alcohol has 1 side of hydrogen bond and a carboxylic acid has 2 sides. So definitely by merely mentioning that, you can see that the other one is able to form 2 hydrogen bonds, the other one. So you are able to see that, okay, now you will write that between compound C and D, we are comparing the boiling point. So we're saying propanoic acid, which is D has a higher boiling point. Why? Because D has 2 sides of hydrogen bond, and then you are saying C has 1 side of hydrogen bond. So that's the first mark that you will say. And then the one with 2 sides has stronger intermolecular force than D, has stronger intermolecular force than C. The third mark, you are saying more energy will be required to overcome intermolecular forces in D than in C. So with that, you are able to answer your question. Is compound B a gas or a liquid at room temperature? Remember, room temperature in us is 25 degrees Celsius. So they are saying go to B, which boils at 56. So you can see that it hasn't boiled yet because room temperature is 25 degrees Celsius. So definitely it's not a gas. It's not a gas because it can only become a gas after boiling. So you know that if it's not a gas, it is a liquid. So you know that compound B is a liquid at room temperature. What is the reason? 56. Its boiling point to only boil at 56, and room temperature was still at 25. We haven't reached the 56 degrees Celsius. That is your 10 mark, and you are able to do that. And with no wasting of time, we'll move to organic reactions. Now, on organic reactions, we are saying now, as I indicated to you, that we are doing addition, we are doing a substitution, we are doing elimination, we are doing oxidation. Sometimes we are referring to it as combustion, and then we are doing esterification. So those are the 5 that we do. Remember, under elimination, we have what is called cracking. cracking as well, which is the breaking down of large organic molecules into smaller, most useful ones. You can't go to write exam without knowing how to define cracking. Now, we are saying USA, these acronyms, always remember them. To say USA, we're saying unsaturated becoming saturated. So when you're having a double bond becoming a single bond, that reaction is called addition. So when you see a double bond, you know that a double bond can only undergo one reaction in terms of our syllabus, and that reaction is addition, which means USA unsaturated, which is in this case a double bond, becoming saturated, which is our single bond. The reaction is called addition. And you have SU. SU stands for when you have saturated becoming unsaturated, we call the reaction elimination, which means the formation of double bonds. In our case, it is our elimination reactions. When you have saturated forming other saturated compounds, the reaction is called substitution. So you got to have that. And we're saying CEDS, which stands for concentrated, is for elimination, and dilute. So when we're using concentrated sodium hydroxide, concentrated strong base, you know that we're going to eliminate. But when we use dilute sodium hydroxide, we're going to, the reaction that we are talking about is substitution. In this case, it will be hydrolysis. So you got to have an understanding of saying CDS. It makes you remember this acronym to say, once I use concentrated sodium hydroxide, I'm eliminating. But once I use dilute sodium hydroxide, I am substituting. And then this was the question that learners were asked 2021 to say too many learners did not attempt this question at all. This question, learners were given butene, they were given compound A, compound B, and 1,2 dibromo-propane. And what learners didn't see here was that this reaction here that took place here is cracking. Remember, the cracking in our syllabus were cracking alkanes. It's alkanes, we break down larger alkanes into smaller, most useful ones. So in this case, we had butene, and for it to become an alkane, it must become an alkane so that it can undergo cracking. So it's important that here it means we have added hydrogen. And when we add hydrogen, we are saying the reaction condition, we use platinum, palladium, or nickel. So we can use those catalysts. So always all the reactions, you must know their reaction conditions. So we have butene forming butane. And when you have butane, it can undergo cracking. And when you say cracking, cracking forms alkene plus alkane. That's what cracking does. It forms an alkene plus alkane, or an alkene plus hydrogen. In this case, alkane is methane. So we know that the other one must be propene. It must be propene. So it's propene plus methane that we formed here. Methane there, we showed it for you there, that we have CH4 that is formed. So this must be cracking. And then when you have propene, you know it undergoes addition. So you can add Br2 there. Immediately when you add Br2, we are going to get 1,2 dibromo-propane. So learn and practice many synthesis reactions, this type of reactions where you are synthesizing and then you're going to form something from something. And then I find them very interesting. And we are saying always know the reaction conditions of these reactions. Now, with no wasting of time, we're able to move as well now. To say now, let's look at activity 4. It's saying compound P is used as a starting reactant in each of the two reactions as shown in the flow diagram below. We're having compound P there. And we're saying this is used as a starting reactant. It's used as a starting reactant. It's used as a starting reactant in each of the two reactions as shown in the flow diagram below. You can see now we're starting there with compound P, which in this case you can see that is C5H11Br. Now, I always say to the learners, it's important that you analyze your question. Look at what is formed when you use dilute sodium hydroxide. Remember what we said, CEDS. When you use dilute, we said the reaction would be substitution. Dilute strong base. So you know that reaction number 1 must be substitution. What did we substitute? We're having a Br, we call it a living group. It's the one that you can substitute. You can see where there is Br. Now we have OL, which is an alcohol, which means we're going to substitute OH, bromo, Br with OH to get that one. But I'm interested mostly on the product that is formed. It's 2-methyl butan 1-ol. That tells you that C5H11Br has a branch. So it cannot be 1-bromo-pentane. It cannot be pentane because it has a branch there. So it means now it must be there is a 2-methyl there and there is a bromo there. So you will see that you are having a 1-bromo. For example, if you look there, you will be having a bromo, and then you are having 4 carbons, which 1-bromo, and then you are having a methyl, say 2-methyl. Then you are having butane, like that. So you are able to see now that that structure that was given there, it can only be 1-bromo without knowing the position. It can be 1-bromo, 2-methyl butane, or 2-bromo, 2-methyl butane. But it cannot be 1-bromo or bromo pentane because of what is forming there. So it's very much important that you look at other products that are formed because it's telling you where I'm coming from. There is a 2-methyl, there's a methyl group in carbon number 2. So the longest carbon chain is not 5 carbons here, it is 4 carbons. That is the thing that I found that it was a challenge for learners. Now, when we use concentrated, we said CEDS. We know this concentrated is for elimination. So here we're eliminating, and there we are substituting. So you can see that this is now hydrolysis. The type of substitution is hydrolysis. We use dilute sodium hydroxide and mild heat. Remember, for substitution we are using mild heat, but for elimination we are using heat. So we use heat here. We heat, but here the heat is mild. So the conditions are important. And then you can see that when we eliminate, we'll have a double bond. We can add HBr, which is your hydrohalogenation. So you are able to analyze that and see all the reactions like that. And then the name of the type of reaction by one, we said is substitution because we're using dilute sodium hydroxide. And then is methyl butan 1-ol a primary, secondary, or tertiary alcohol? So you can see that the 1-ol there, in terms of the OH, the carbon which it is bonded to is a primary carbon because that is the carbon atom bonded to the OH is bonded to only one other carbon. How many other carbons? One other carbon. So we're calling it primary alcohol. Write down the structural formula of compound P. So you must be able to write the structural formula of compound P, and then you are led by that one, which is 2-methyl butan 1-ol. And then you are just putting in carbon number 1, you are having the bromo there. Then you are able to show your bromo in that carbon. Then you'll get 1 mark for your bromo, 1 mark for the substituent, and 1 mark for the whole structure. So it's important that you are able to draw the entire structure. Even if you were to lose marks, but you won't lose marks, you know it's butan 1-ol here. So you know that here you have 4 carbons in the longest chain. So you will definitely get a 1 mark for identifying that. You will get another mark for seeing that in carbon number 2, we have a methyl. And then the last mark is for the to see that we have bromo in that carbon, and then that becomes your structure. So I hope you got that, and it will be able to help you. Name the type of reaction represented by 2. Remember, we said concentrated is for elimination. Definitely, this must be elimination. The type of reaction is elimination. Or you can just say dehydrohalogenation will take the answer, or dehydrobromination. But the type of reaction is elimination. The type of elimination is what we are removing, which is dehydrohalogenation or dehydrobromination. To which homologous series does compound Q belong? Definitely, because we are eliminating, we are forming unsaturated, so it must be an alkene. Now, we're able to move on with the question. Name the type of reaction represented by reaction 3. So you can see that as long as you're having a double bond there, you're having an alkene. It must be addition reaction. It must be addition reaction because you're having an alkene there. Now, write down the IUPAC name of compound R. So now remember, you had an alkene here, with a 2 in carbon number 2, you had a methyl and you had a double bond, then you have to write the name of the structure, which is 2-bromo 2-methyl butane after you have added. So at the end of the day, that is what you will be having. Now, with no waste of time, we can look at cracking. Remember what I said about cracking, to say this is a chemical process in which longer chain hydrocarbons molecules are broken down to shorter, more useful molecules. And they were saying this cracking, it can be thermal cracking, where we're using high temperature and high pressure, or it can be catalytic cracking, where we're using the catalyst. Now, in terms of alkene, I told you that our cracking, it forms alkane and an alkene, or an alkene and a hydrogen. For example, we're given there ethane. It can undergo cracking, elimination, where we are eliminating hydrogen, dehydrogenation, and then it will form an alkene and hydrogen. But look, when you're having butane, for example, you can eliminate the first carbon, then you'll get methane and propene. So always alkane, alkene. We can even go and crack it in the middle, then we'll get you'll get ethene and ethane. And then as well, you can go and remove only the hydrogens, and then you get butene there and hydrogen. So always know that as long as it's cracking, you can crack the structure. It can be 1 carbon, 2 carbons, 3 carbons, depending on what you are doing. But at the end of the day, what is on the left is the same as what is on the right-hand side, is equals to what is in the product side when you check the number of carbons and hydrogens. So remember that as always. Now, the last reaction, as we leave the reactions now, is combustion. And then we are saying combustion, which is oxidation reactions. We are saying is the reaction of alkanes like C4H10 when it's reacting with oxygen. So if I can move like that, sorry for that, to say you are having your butane, which is C4H10, and then it's reacting with oxygen to form carbon dioxide plus water. Before you do anything, already you have a mark for reactants and products. You are left with 1 mark for balancing the reaction. And we are simply saying that now, if you come here and say this is N plus 1, at least you are going somewhere, and you can put before the O2 there, you can say 3N plus 1 over 2, just before O2, you can put that. And then you are able to balance the whole reaction. If we do like that, and you say NCO2 plus N plus 1 water. And then N is the number of carbons. So you're simply saying, okay, C4H10 plus N is 4. 3 times 4 plus 1 gives you 13. So you're able to get 13 over 2. O2 gives us N is 4. CO2. N plus 1 is 4 plus 1, which is 5. Water. And then you multiply the entire equation by 2 to get 2C4H10 plus 13O2, forming 8 carbon dioxide plus 10 water. And then that's it. And then you are able to balance that reaction. So it's very much important that you are able to write a balanced equation. Don't forget, this is energy is given out. So energy is one of the product as well. So as you balance those reactions. So please practice combustion so that any question that comes under this oxidation, you are able to answer. Now, I wanted us to look at the empirical formula as well, to say empirical formula and molecular formula. Last year, there were questions based on this one. And then here we're saying you can be given the mass or the percentage. What you have to do is to convert your mass or your percent to moles. After you have done that, you must divide all the mole values by the smallest mole. You divide all the moles that you got by the smallest mole. After that, you round or multiply to get whole numbers. Remember, empirical formula we are saying is the simplest whole number ratio, the simplest whole number ratio that we are having. That is your empirical formula. And then if molar mass is given, you can be able to determine the molecular formula. How do you do that? You will take the molar mass, you divide it by empirical formula. The empirical formula that you got, you divide its mass, the mass of your empirical formula. You take the molar mass that is given, you divide by the empirical formula mass. So I felt that it's important that we demonstrate this one using an example. And even last year we had a question that was based on this one. I find it good that even in the marking guideline we had a table like this, hence using a table is user friendly. To say, you will say we're having carbon, hydrogen, and oxygen, and when we're having those, we're given the mass, so we're saying percentage by mass. So percentage by mass, that must be 100 gram. Our 100% is our 100 gram. Then you write the percentages by mass, which is 72.04 grams, 10.42 grams, 27.54 grams. Then you divide them by, so you are having the mass, then you list their molar mass to say what is the molar mass of carbon is 12. Molar mass of hydrogen 1 or 1.008. Molar mass of oxygen 16. So you are able now to say, okay, I'm having the mass, I'm having the molar mass, I can calculate the number of moles. How do I do that? I will say mass over molar mass. So you will take your mass, 62.04 divided by molar mass, is 2, and then you get 5.17. You take 10.42 divided by 1, you get 10.42. You take your 27.54 divided by 16, you got your 1.72. And the next step was to divide by the smallest number of moles, which is 1.72. And when you divide, you will get 1, you will get 3, and 3. You'll get 6 here. Sorry for that. You'll get 6 here, and you get your 3 there. Then you are able to see that you are getting 361 as your empirical formula. So as you write your empirical formula, you would say C3H6O. Oxygen is only 1, H is 6, carbon is 3. That is your empirical formula. Now you are able to move from empirical formula to molecular formula if you are given the molar mass. The molar mass was given as 116. So we have our molar mass as 116. So what you will just do, you get the ratio of the molar mass and the empirical formula mass. So once you take the molar mass, you divide it by empirical formula mass, you are able to get your N, which is your ratio between those two. In this case, when you do that, you'll say 116, which is your molar mass, by your empirical formula mass, you get 2. So you multiply N by your empirical formula. You take your empirical formula, you multiply it by N, which is the ratio of your molar mass and your empirical formula mass, which in this case it was 2. So when you multiply this by 2, you get C6H12O2, which is hexanoic acid. So you are able to do that, and it's important that you know this. Remember, we're having half of the paper, which is organic, a lot of marks from organic. So we're saying spend time there and remember that. Now, when I move, we look at the basic stoichiometric calculations to say this is very much important now, because learners lose marks in terms of this one, to say when I'm given mass, I must be able to calculate the number of moles. That is the simple task that we are asking of you. To say, if you are given mass, you must be able to calculate the number of moles. If you are given volume under standard conditions, STP, standard temperature and pressure, which in this case, the temperature of 0 degrees Celsius and pressure of 101.3 kilopascals, you must be able to utilize that formula of N equals to V over Vm. And then you are able to use the molar volume of 22.4. Sometimes you'll be given a molar volume maybe of 24, which is at room temperature. Still, you can calculate, use N equals to V over Vm using that molar volume that you are given. But at different temperature, the molar volume won't be 22.4. For example, it's only 22.4 at temperature of 0 degrees or a temperature of 273 kelvins. Now, at room temperature, which is 298 kelvins, you will find that your molar volume is 24 cubic decimeter, so per mole. So it's important that you always have that information in your mind. Sometimes you'll be given the particles, you must be able to calculate the number of moles. Or sometimes you'll be given the concentration and volume, you must be able to calculate the number of moles. So we're saying, know that whatever you are given, they only bridge for you, because if, for example, we gave you say A plus B forming C, so the main thing, if now we give you the mass of A, which is solid, for example, we give you the mass of A, you must be able to calculate the number of moles of A and because it's only when you have the number of moles that you can be able to move from this one to the other one using the mole ratio. So the only bridge between this A and this one is the mole ratio. So it's important that when you are given the mass, you are able to calculate the number of moles. When you have the number of moles, use the mole ratio to determine the other given, can be reactants or products that you are given. So that's what we are saying, to say always check, but the only way of moving from A to B is through the mole ratio. Mole ratio will help us to use information of A in order for us to get B. So we're saying get the number of moles. After getting the number of moles, be able now to determine the unknown using the mole ratio. So that's what we are doing. And we're saying, as you write your papers, always think about the mole ratio, as it is important. The other thing that I didn't want to leave out is the issue of percentage purity. To say percentage purity, important as well. We are saying here is the total mass of the pure substance divided by the total mass of the impure substance, which is the pure mass divided by impure mass times 100. That's how you calculate the percentage purity. In this case, we're given the total impure as 5 grams of sodium carbonate, and we find that the pure of sodium carbonate was 4.25. And the question was calculate percentage purity, which in that case, you will simply say pure mass divided by total impure multiplied by 100, and then you are able to get your percentage. So if you find a question that talks to the percentage purity, definitely you must do it. Now, let's look at rates of reactions. To say, when it comes to rates of reactions, the first thing that we always emphasizing is the definition of rate of reactions. To say, rate of reaction is the change in concentration of reactants or products per unit time. Please always get the definition correct. And we are saying that now you are able to know the graph of reactants and the graph of products. The graph of reactants and the graph of products, you are able to differentiate between them, because we are saying as we start the reaction, we have reactants only. So the reactants would always start with something, but with the products, we're starting from 0 because we don't have products there. Hence, the graphs that are moving like that, you will see that these are the graphs of the products, and the graphs that are decreasing are the graphs of reactants. And how do we collect our volume, our gas? We're using the gas syringe. Hence, we are saying if this is the graph of the volume of gas, which in this case is H2, is a product, it will start from 0 and it increases until where the curve flattens, we're saying the reaction has reached completion, or the reaction has stopped. So have that in your mind. Now, remember we said there are factors that affect the rate of reaction, and those factors, which is temperature, concentration, surface area, nature of reactants, catalyst, and pressure, 6 of them. Always remember how they affect the rate of reaction. So we're saying, as for the fastest reaction, the curve becomes more steeper. So you have the steeper the line, the greater the reaction rate. So if you are given a curve, the green one, and we say draw the curve when the temperature is increased, obviously the curve must become more steeper to show that we have increased. When the graph becomes more steeper, we're saying we have increased the rate of reaction. So the faster reaction, which is this one now, it will be able to, it becomes horizontal sooner. So you can see that it's horizontal from there. So it means that the reaction reaches completion faster than the one where the factor was not increased. So this graph, you can use it to show the effect of increasing temperature, effect of increasing concentration, effect of increasing surface area. All those will increase the rate of direction, meaning that the graph will become more steeper, and then when it becomes more steeper, it will be more horizontal sooner to show that it completes faster. But in terms of the volume of gas produced, you can see that it is the same amount of gas produced. Now, when it comes to collision theory, remember with collision theory, we are focusing on this one to say the collision theory says there are 3 conditions that must be met for a reaction to occur. We're saying the reactants must be able to collide effectively with one another, and we're saying these reactants must have enough kinetic energy, and they must have correct orientation. So it's three things that I'm looking at there to say the reactants must collide, they must collide with enough kinetic energy, and they must have correct orientation. If we have that, the reaction now will be effective. We'll have effective collision. What is effective collision? We're saying this is the collision that leads to the formation of products. Now, we look at the Maxwell-Boltzmann distribution curves. Very much important that you understand all of them. Now, know that for temperature, when we increase temperature, you see what happens to the graph. It shifts. The graph shifts to the right and touches the original graph. So it shifts to the right, T2. It shifts to the right. Hence, we're saying the graph has dropped. It shifts and then it touches the other graph. It shifts and touches. That is the graph of temperature. And then what do we say when we say use collision theory to explain the effect of increasing temperature? We're saying increasing temperature increase the average kinetic energy of particles. It increases the average kinetic energy of particles. And then we're saying when we so doing, we're going to increase. We're going to have more particles with more effective collision per unit time. More effective collision per unit time. You can't write MECPUT. I'm just saying it so that you are able to remember how easy to write it, to say, okay, the first bullet, we said when we increase temperature, we increase the average kinetic energy of the particles. The second bullet, remember we're using bullets. The second bullet, we're saying more effective collision per unit time in full. And then you are able to say we're going to increase the rate of reaction. You can say we'll have more particles with kinetic energy greater or equals to activation energy. So those bullets, please make sure that you are able to show all of them to say when we increase temperature, we increase the average kinetic energy of particles, more effective in full, more effective collision per unit time. It's a 6-letter word. We're emphasizing that. And we are saying you will increase the rate of reaction. We'll have more particles with kinetic energy that is equal, greater, or equals to activation energy. Everything written in full there, you are able to collect your marks. That's how you will deal with increasing temperature under collision theory using Maxwell-Boltzmann distribution curve. Now, if we look at the graph of concentration, it now becomes, it is on top of the original graph, because when we increase concentration from here, concentration is N over V. So when we increase concentration, we're increasing the number of particles. When we increase concentration, we're increasing the number of particles per unit volume. So that is the first bullet. You will say increase in concentration, increase the number of particles per unit volume. It increases the number of particles, which is that N. It increases the number of particles per unit volume. Don't forget. And then what is bullet number 2? More effective collision per unit time, which I said MECPUT for you to remember, but it's just an acronym. You must write it in full to say more effective collision per unit time. Bullet number 3, we said, okay, now we're going to have increase in the rate of reaction. And then you can see here, we still have more particles with energy or kinetic energy greater or equals to activation energy. So you can see that you can follow that order, and then the conclusion is always that it will increase the rate of reaction. But when we add a catalyst, remember what a catalyst does? It lowers, it provides, catalysts provide an alternate pathway, provides an alternate pathway of lower activation energy.